Hi, this is the fourth lesson of topic 12 on magnetism and the motor effect. And this lesson is about the calculations involved when considering Fleming's left-hand rule. If you're not sure about what Fleming's left-hand rule is, go back and watch lesson 3 on the motor effect. Now, Fleming's left-hand rule considers the force experienced by a current-carrying wire in a magnetic field. But what dictates the magnitude or the size of this force? Let's take a look at some isolated examples. Take a look at these two diagrams. They differ very slightly. On top we have diagram A, and below we have diagram B. In the middle of these two magnets, we have a current carrying wire. Which wire do you think experiences a greater force? Pause the video and think. So the answer is B. And that's because the greater the current, the greater the force a current carrying wire will experience. Let's take a look at another example. In this case, which wire will experience a greater force? In diagram A, we have a current carrying wire passing through a magnetic field. However, in diagram B, our current carrying wire is only partially passing through this magnetic field. So which one experiences a greater force? Pause the video and think. So once again, our answer is B. And that's because the greater the length of a wire within a magnetic field, the greater the force the current carrying wire will experience. So this is the second factor which influences the force experienced. And let's take a look at one more. We can see there's a clear difference between diagram A and diagram B. In which case do you think the wire experiences a greater force? Pause the video and think. So as we can see, in diagram B, there are far more magnetic field lines compared to diagram A. We have 5 magnetic field lines at the bottom and only 3 at the top. As a result, these lines are far more densely packed compared to the ones at the top. The number of field lines in an area shows the strength of the magnetic field. This is known as magnetic flux density. And this shows the strength of the magnetic field. And the greater the magnetic field, the greater the force a current carrying wire experiences. Therefore, we can say that because the current is the same in both cases, and the length of the wire in the magnetic field is the same in both cases, diagram B shows a wire that experiences a greater force. Now it's time to calculate the force experienced by a current carrying wire in a magnetic field. But to calculate this force, to calculate the size or the magnitude of this force, what could the equation be? Based on what we've just learned, what are the factors that influence the force experienced by this wire? And based on that, what do you think the equation could be? Pause the video and think. The force experienced is dependent on 3 things. The first is the magnetic flux density, which shows the magnetic field strength. The second is the current. And the third is the length of the wire present in the magnetic field. So our force is equal to magnetic flux density times current times length. Our force can be represented by F. Our magnetic flux density is denoted by B, Current, as we know, is represented by I, and the length of the wire is represented by a lowercase l. So that's F equals B times I times L. As we know from topic 2, force is measured in newtons. Magnetic flux density is measured in Tesla. Current is measured in amps or amperes. And length is measured in meters. Make sure you've taken all this down as it's extremely important. Now let's try some questions. So, let's try it together. In this case, a 10 centimeter length of wire, that's our length, carries a current of 3 amps, that's our current, sits inside a magnetic field. The current flows at 90 degrees to the direction of the magnetic field. Because it flows perpendicular or right angle to the direction of the magnetic field, we know that it follows Fleming's left-hand rule. It experiences a force of 0.12 newtons from the motor effect. Calculate the magnetic flux density. Okay, so with any question, the first thing we're going to do is write the equation. F equals B times I times L. Next, we're going to substitute into our equation. Our force is 0.12 newtons. Our magnetic flux density is still unknown, so we'll leave that as B. The value of current is 3 amps. And our length is 10 centimeters. Now you may have noticed that our length is in centimeters, not meters, so we need to convert it. Let's do that. So we still have 0.12 newtons. However, now instead of 10 centimeters, we're going to write 0.1 meters. That's because there's 100 centimeters in 1 meter. Next, we are going to rearrange and solve for B, solving for our magnetic flux density. We're going to divide by 3, and we're also going to divide by 0.1 on both sides. That gives us 0.12 divided by 3 times 0.1, which gives us B. And when we put that in our calculator, we get the answer of 0.4 Tesla. Let's try another. Pause the video and attempt this question. Okay, so a conductor of length 40 centimeters, so we know 40 centimeters is our length, is situated perpendicularly or 90 degrees in a magnetic field of flux density 8 Tesla. So that's our magnetic flux density. The current flowing through the wire is 12 milliamps, that's our current there. And we need to find or calculate the force. So once again, we're going to follow the exact same steps. First, we're going to write out our equation. Next, we're going to substitute. Our force is still unknown, so we can leave it as F. Our magnetic flux density is 8 Tesla. The current is 12 milliamps. And our length is 40 centimeters. Now you might be able to see that there are 2 conversions we need to do in this case. We need to convert from centimeters to meters, and we also need to convert from milliamps to amps. So let's do that now. 12 milliamps is 12 times 10 to the minus 3. And 40 centimeters is very simply 0.4 meters. Now we can find that force is equal to 0.0384 newtons. Make sure you include the unit at the end. Let's try one more. This one's a bit more difficult, and you may need to draw the question out to help you answer it. Pause the video and have a go. So, the current flowing through a wire is 3 amps. The coil forms a square with sides 5 centimeters long. Calculate the total force acting on the wires that are perpendicular to the 0.2 Tesla magnetic field. Now, the first thing we're going to do with a question like this is draw it out. This represents the north pole of a magnet, and this represents the south pole of a magnet. Between the north and south pole, you'll have magnetic field lines that look like this. Now, the current flowing through our wire is 3 amps, and the coil forms a square. So let's draw that square out. So that's our coil of wire, our square coil of wire. And its lengths are 5 centimeters long. Calculate the total force acting on the wires that are perpendicular to the 0.2 Tesla magnetic field. From this diagram, which wires are perpendicular? Pause the video and think. So as we can see, these wires are perpendicular, and these wires are parallel to the magnetic field. We can see that the magnetic field travels in this direction. And these wires are perpendicular, as shown by this right angle. So, considering this, let's now complete our question. The first thing we're going to do is write the equation. F equals B times I times L. Our force is unknown, so I'll leave that as F. Our magnetic flux density is 0.2 Tesla. Our current is 3 amps. And our length, in this case, is 10 centimeters. That's because the total length of wire present in the magnetic field that's perpendicular to it is 10 centimeters. 5 centimeters here and 5 centimeters here. 10 centimeters. The next step is we need to convert from centimeters to meters. And as we know, 10 centimeters is 0.1 meters. And the final step is to simply substitute these values into our calculator. And we get an answer of 0.06 newtons. And that's it. I hope this lesson has been challenging and useful. If you have any questions, please do ask.